Okay, so we at this point have talked about microevolution, and just to refresh your memory, the idea of microevolution is that you can have these small genetic changes over time in a group of organisms, and one of the best examples of microevolution is how a population of bacteria as in terms of an infection might change over time in your body. So if you have an infection of some sort and you take an antibiotic but you don't completely finish it all off, then that bacteria could potentially, as a group, could change genetically over time and become more resistant. And this happens in a lot of things, in bacteria, insects, and so forth. The idea now with macroevolution is sort of the same concept, but if you extend that over much longer periods of time, the idea with macroevolution is that you can get larger amounts of genetic change over time that could result in new species, for example, or new groups of organisms. Now, the way that we sort of show or depict the evolutionary relationship of different organisms based on their evolutionary history and their similarities and differences is, there's many of them, but one of the common ones now is this idea called a cladogram. So in a cladogram, they basically, you take the groups of organisms, whatever they might be, that you want to show how they're related evolutionarily, and you place them on there, and then you have these branching patterns. And what the branching patterns tell you is that wherever there's a split, like you see there, the idea is that there was some evolutionary event that occurred at this point and this point and this point that led to a difference in whatever those end up becoming. So in this particular picture, for example, they're showing you that a long time ago, way back at this point, there was some ancestor that eventually the ancestors split into two different groups, and one group of those became these organisms over here, the dinosaurs, the birds, and the crocodiles, and then the ancestors to those many generations later gave rise to the placental mammals, which are things like us and rabbits and other animals that have a placenta, and marsupials such as kangaroos, those that have a pouch typically and have their offspring or baby, a real small baby that lives inside that pouch until it grows up. And then the monotremes, which are the egg-laying mammals, which there's only two of them that are known right now in Australia, is where they occur. So what you know about these splits, or what the splits mean, is that there's an evolutionary event that's taken place, and it doesn't really tell you how long ago that took place, but instead the only thing you can get from that event is that that split had to have happened after this split, for example. Okay, so that's the idea of a cladogram. And there are many different examples of macroevolution that we can see in the fossil record, for example, of organisms. And by taking these organisms and by placing them in a organization of when you might find them, for example, if you have a canyon in which there have been layers deposited over long periods of time or carved out, and you find fossils here versus here versus here and all the way up, you can have an idea of about how old they are relative to each other. And from that, by looking at fossils and by comparing fossils of organisms that we find at different time periods, and by comparing how similar or dissimilar certain organisms are, we have come up with what we call this geological time scale that gives you an idea of when certain events happen. Now, in this particular course, we're going to really only worry about the four big major eras, which are the Precambrian, the Paleozoic, Mesozoic, and Cenozoic. So the rest of this chart here gives you some more finer details about when certain things happen. For example, it's believed that the Earth formed about 4.6 billion years ago, and that the first animal fossils appear around 600 million years ago. So this gives you an idea, and starting from here, this is older, and as you move this direction, this is newer. So this is modern historic times here in the early part of the Cenozoic. One of the things we can also do is compare how old something is, not just based on where they find it in a say a level of sedimentary rock, which is layers of rock laid down by sediments, but we could also do what's called radioactive dating, in which you can measure how old a particular rock or organism is based on a certain isotope of a particular radioactive element. So I'll give you an example here. One of them is carbon-14, and it is believed that carbon-14 has a pretty depictable rate of decay, which is about 5,600 years. So half-life of about 5,600 years, which means that if you had an organism that was alive and eating food, it would be consuming whatever food it was eating, and the amount of carbon-14, which is found in the air, would constantly be replaced as the organism ate. But once the organism dies, the animal no longer takes in food, and the carbon-14, which is an unstable isotope of carbon-14, would decay. So if you have an organism of a certain size, you can estimate how much carbon-14 it should have, and then you can actually measure how much it has, and by comparing that, you can figure out how old something is. Now, carbon-14, I'll show you this a little more in detail in a second. Carbon-14 has a half-life of about 5,600 years, so it turns out that as something decays, and something's over about 50,000 years, carbon-14 no longer works very well because there's so little left. But there are other things we can use. One of them, for example, is uranium-238, and that has a half-life of 4.5 billion years. So they have, depending on the isotope, they have different levels of radioactive decay, and you can measure things that are older. So the idea of carbon-14 is this. If you assume that you have an animal, and the animal is a particular size, and based on the amount of carbon-14 in the air, that organism, you would assume, right when it dies, has about 100% of the amount of carbon-14 that you would get in the air. Okay, so it remains about the same right when it dies. But because, once again, carbon-14 is unstable, it's decaying. So 5,600 years later, you would expect the carbon-14 that about half of the isotopes of that will decay and will no longer be carbon-14. So you took that whole thing of carbon-14, and it takes about 5,600 years, you would expect, to lose about half of it. Now, the next thing is, this is what you have left, okay? So the rate of carbon-14 decay seems to be pretty consistent, which means that how much is going to be left in another 5,600 years? Well, because the rate of decay does not change, what happens is you expect in another half-life, so one half-life plus two half-lives, if you add those together, that's a total of 11,200 years, you will lose another half. So you're always losing half, even though this half is smaller in size than this half. The rate at which it decays stays the same. So what you're really measuring is, you're measuring the amount that has decayed based on a consistent rate. So you're always losing half, which means at this point you have what the original amount would be about 25%. So at this point you have 25% of the original amount of carbon-14, which is 2 half-lives. If you were to lose another half of that, which would be like if you lost this little piece in here, right in there, then that would be another half-life. as well. That would be 3 half-lives. You would add 5,600 to that, and that would give you something like 16,800, I believe, if I'm doing the math correctly on that. So that's how half-life problems work.